So because there are two revolute joint, and you know that dealing with revolute joint, you need to know from which point you have to look at it, and there's sine, cosine showing up. I'll help you to with the reference frames, all right, with the directions, and then from there I want you to think about it for about 5 to 8 minutes. All right, see how far you can go. So for the reference frame, we know that we start from the first joint. So this is going to be Z1, this is going to be Z2, and then I'm gonna say that my Z0 also gonna be in this direction, right? And then if you remember, we can define the direction of x-axis. So these two are parallel. I'm gonna say x1 is here, then I'm gonna follow x2, and then this is going to be my x0. And then from the right-hand rule, you're gonna find your y. This is y0, y1, and this is y2. They make it very simple. And you see that in this example, you have links, but you don't have their distance, right? You don't know what is the length of the link. Just put variable A1, B1, whatever you like. I'm gonna say this is A1, this is A2, this is A3, A4, if I needed them. All right, so I know that there will be some distance. And this is my end effector, so I'm gonna follow my last frame. So this is I'm gonna call it X3, Z3, Y3, and I'm gonna mention this is the end effector frame. So I know the position of end effector frame. So find the inverse kinematic expression. if you started from this what you're planning, really from the top, you will see something like this, right? Now, we know what H2 is, what A4 is, right? We can call this, let's say, R, all right? Say R1. Do we know what R1 is? Yes. Yes.
Shouldn't the reference bridge be rotating as the rotates?
No reference. So here you are showing at home position, right? So again, this is to show this rotates this way. Oh. It's just to show so you can actually then be able to measure this. Because theta could be 0, so right now. Back to my question. Do we know what R1 is? Yes. So we know because we know where this is, right? And then we know where this is, x0, 3, and y0. So we actually know what R1 is. So x0, 3 squared plus y0, 3 squared. Now we know that. So why is that good? Because if you look at from the usual suspect that we reviewed last class, you might not be able to find these. You see that this is that's why this is the hardest problem. It has two revolutions. You remember I told you you need to know one more relationship from your trig to be able to solve this. What was that? Law of cosine, right? So now you can see, oh, I have R1, I have A1, I have A4, and I have theta 1, theta 2, so I can write a relationship for that, right? So usually when you have revolute joints, only revolute joints, or two revolute back to back, and then you know that you have to do this because they will be dependent, especially if they show in the same plane. If they were in different plane, that's a different scenario. Now they are in the same plane. So first, let's see that if we need to use law of cosine right away, or can we find more relationship here? So I'm going to bring this outside. R1, A4, A2, right? So this was theta 1, and then let's concentrate on that for now. Can I say this, if this is phi1 and this is phi2, theta 1 is phi2 minus phi1? Can I say phi2 is tangent inverse of y03 over x03? Yes. So what I'm doing, I'm trying to relate the information I have from the end vector to this configuration right now, right? Now, I can now use law of cosine, right? I have this to be phi1, right? So I can write the law of cosine for phi1. I already have phi2. I can find the one, right? So just a reminder what law of cosine was. I'm gonna keep this kind of seamless so I can actually see what happened here. Keep it in your cheat sheet, law of cosine. So. For this example, A4 squared is A2 squared plus R1 squared minus 2A2 R1 cosine of phi1, right? I have everything else. I can just write cosine inverse of that relationship. Then I have what phi1 is. So phi1 is cosine inverse of A4 squared minus A2 squared minus R1 squared divided by 2A2 R1. And we have all of those, so we know what phi1 is. we know what phi 2 is. So we have our theta 1. So theta 1 is, as we said here, phi 2, which was tangent inverse of this. Okay, paste here, minus phi 1, copy, paste. All right. How many joint variable did we have? 2. We found a relationship for one of them, theta 1. Now we need to find a relationship for theta 2. So from this, I'm gonna just copy this and bring down here. This time is the same thing. I'm just trying to utilize it the best way possible. So this is your theta 2, correct? That was theta 2. You all agree? Now, how can I find theta 2? Let's say, yeah, how can I find theta 2? Yes.
So you take for theta 2, what, 30 degrees, theta 2, all the way back to the other.
Call it theta phi 3.
Yeah, phi 3, we can find the constant straight angle.
Yeah, exactly. So I know that theta 2 plus that phi 3 is going to be 180, right? So theta 2 is going to be 180 minus phi 3. How do I find phi 3? Another law of cosine, right? It's still the same thing. I can just now this time write law of cosine for this one. So basically I have phi 3. So again, law of cosine. I know R1 squared is A2 squared plus A4 squared minus 2A1, A2, sorry, A4 cosine of phi3. So phi3 is cosine inverse of A2, A4. Great. Well, that's it. Theta 2 is 180 degrees. Let's be correct. Minus this guy. Copy, paste, style, green, matches. All right, that's the second angle. So I found inverse kinematic relationship for both of these angles. All right, so you will be given the position of the end effector. You have the configuration of your robot, meaning the length of the links. You plug it in, and you have that. Now, if you think about simulation and writing the code, so you will have a vector that has all the end positions, and you keep putting in this equation. So imagine you're trying to move, you're trying to grab, imagine I'm trying to grab someone's gonna come here and ask for it. I'm trying to grab the eraser with this robot, right? I know this position, x0, y0, z0. I can go, well, I can know what is the joint angles and then drive it. But also, if you think about point to point, if you're here, you know what is the next point, you go to it. You know the next point, you go to it. You know the next point, you just go to it. This is called point to point pathfinding. So for point to point pathfinding, all you have to do is solve the inverse kinematic between the 2 points. Now the 2 points can be as close or as far, right? Depending on what's the resolution of the path that you're taking or resolution of your simulation, let's say. So you can drive your angle small, little by little, and smooth. Does that make sense? So, the application of this in the system that, or in the robot application you're using is important. All of you know the theory. The theory on its own doesn't do anything. It needs the human in the loop to understand and use this theory properly. So when we solve inverse kinematic, you're always solving forward kinematic. Why? So I try to solve inverse kinematic and say, okay, go there. And I check where the forward kinematic is. If there was an error, I'm going to solve it again to reach the position that I want. Does that make sense? So every time you're solving inverse kinematic, you have to eventually solve a forward kinematic as well. Just to make sure that you ended up where you said you will. We're running the robot into expensive thing. Okay. All right. So this would be the most difficult example you'll get for inverse kinematic. Now, imagine I throw a prismatic into it. So there's prismatic, just there's a B showing up and it'll be distance, right? Always add A plus B2. The length of the link will increase, nothing else will change. Any questions on inverse kinematic? From the geometrical solution, we have two more. But I like this because you can actually see what is happening, even though if you're not very good at trig, you still can see what is happening, right? I'll take that as Dr. I'll study later and hopefully I'll understand. It's okay. I think that's so. Sometimes I think why they don't answer my question. Then I remember when I was a student, I did exactly the same thing you did. I studied later, so study later. But you remember. All right. So the other two methods, if you remember, one was the analytical method of solving inverse kinematic, and the numerical method of solving inverse kinematic. Numerical method is not going to be in your exam. You will have to use it probably for one of your PA assignments. And when it comes to solving PA assignment, I usually let you use whatever you want, as long as the solution is correct, unless I ask a method. So if you want to solve it analytically, with your metric, you might guess. But numerical, usually what you will use more complicated scenarios. Now for the inverse kinematic, this is the Kumar robot, and I'm using this example just to show you. Now, which one of you have the book? Raise your hand. There is a link, right? You don't have to pay for it, right? So for this part, I want you to look at the book because I'm not going to write down all the equation and take the class time, bore myself, and you'll forget about it. You need to go and check the book. All right? When we think about analytical method of solving inverse kinematic, we will divide it into two different problems. We will say that we will solve the inverse position and inverse orientation. So far, everything we solve in geometrical method, we just talked about the position, right? Because robots are usually simple enough that they are either planar or the plane is not too complicated. The robots are not too complicated and you can predict the orientation just by the knowledge you have. For more complicated robot, for complicated cases, especially if you have the wrist attached, then you have to solve for inverse orientation because you actually don't know where things will end up. All right. For the inverse position, it's pretty straightforward. It's just like what we did. For inverse orientation is a bit more complicated. So for Puma robot, is a 6-arm, 6R arm. 3 of them are the shoulder, elbow, and the base, shoulder, and elbow. So you rotate, the robot is rotating here, 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 and here. Now you see there is a wrist, right? 1, 2, 3, sorry. Shoulder, elbow, and the wrist, just the end of it. You can put any kind of wrist you want, right? So that is 3R. The 3 other R are the end of it. So it will rotate in all directions as well. We usually separate these two and solve them separately. Do you remember why we could do that? I talked about it. Why we can separate the risk, like the end effector from the risk? What's that? Because this will tell us the orientation, right? For the position, we need to know where the risk will end up. Usually the risk has something that has like identify orientation or would be grabber. So the risk position doesn't move, right? You just do the grabbing of the object or orienting. Like if it was a camera, you would rotate it to look at something. The position won't change. So we will separate them to solve position and orientation. So for position, you're gonna cut off here. So we're gonna do 1, 2, 3 off. If you have done, you can solve that as geometric also, because you already done it. It's all in the same plane. If you look at it, base, shoulder, elbow, okay. This actually is going to look at base, the shoulder, the elbow. 1R, so this is the Z direction, this is the Z direction, this is the Z direction, right? And we have a link that we can say we're working with. We call this subsystem, so we are solving this as sub-problem, sorry, not subsystem, sub-problem. Problem 1 is the position, problem 2 is orientation. Now, the schematic you're seeing is basically what we have done in our geometry. The only difference is that there's 3R. 2 of them are in the same. So this is Z, right? So let's say this is Z1, Z2, Z3, and this is Z1. Now, you can write sine cosine relationship and connect and find 3 expressions for theta 1, theta 2, theta 3. So 3 expressions, 3 variables, you solve it. All right? We can start from saying that, okay, let's assume that our PC is not 0, so the robot is not back onto its own origin. So you can look from top and find Py and Px, and you know, we just did that, correct? And then once you're done, you go from the other side and solve for the third one. So I'm sure that, like, at least with the geometrical problem is solved, you should be very good on analyzing this part because you've done it already. Now, how do we go about the orientation problem? Well, I'm not going to show you. I should think about it. What does the orientation problem mean? Like, what is it that you're solving? Don't look at the, oh, that's the book. No, he was looking at the book. And you were looking at the book. Good. Good, because this is an example from the book. So I wanted you to go and study. But think about the orientation problem, the sub-problem for orientation. How can we solve? From the position problem, what did we find? I don't want to say this, we have 3, right? We plug in the values, we have 3. The robot itself has how many variables, string variables? 6. We solve 3 of them, right? So if you think about the forward kinematic expression, you have half of it. The only thing you don't have is theta 4, theta 5, and theta 6. Correct? We have to find that. So our problem, our solved problem is already shorter than it would have been from the beginning, because we already know 3 of the thetas. So if we can write the forward kinematic expression, you could either go DOE method or DH table method. Since your book doesn't teach DH table, they introduce POE. You could go either way. All right. So you remember the forward kinematic expression, right? So if you have theta 1, theta 2, theta 3, you have e to the power of bracket S1 all the way to bracket S2. So that is known. Your M is known, which is the initial position. You only need to find 3 of them. So you can manipulate that. So you have this part. You only need to find this. Yes. That's the thing. Because you know where the position is, right? Oh. It's the inverse kinematic, so you know the final orientation. So you can actually write theta, T of theta. I'm gonna, good question. So this is your T of theta because it's the inverse kinematic problem. We know what is the final position orientation. Now, all we have to do is this 3. All right? If you look back at the robot, if you go back at the robot, there are 3 R's, right? They're along the principal axis. What information can we have by looking at a robot knowing that fact? We know our omegas, right? We know omega 1, omega 2, omega 4, omega 5, omega 6. If you think about what would go into S4, S5, omegas, do you have any V from a prismatic zone? No, right? So basically, we will end up with, oh, we know our omegas. Only thing we're missing is how much is rotating. Theta 4, theta 5, theta 6. So we change that to rotation. Why can't I write this? Why can't I say instead of so what I did is here. Instead of this, I wrote rotation Z and theta 4, saying that I know what Z is. Why can I do that? Why can't I change it to rotation? Exam 1. Remember exponential coordinates? That's the definition of exponential coordinates. If you know the direction of the rotation, right? Axis angle is as if it was a rotation about that axis for that angle. So I'm swapping that to something I'm familiar. I already have half of the solution. So what does this look like? Do I know how does rotation about the axis theta 4 look like? This is a standard rotation. The 3 by 3 matrix, it just has theta in it. Same. I can actually solve it. The 3 by 3 variables, I can find. Right, because this side is equal to that side, which is, I can take the rotation part of that, correct? Just here, this part, you might say this is 4 by 4. Okay, but it has the rotation part. I can grab the rotation and say 3 by 3 equal to 3 by 3 over here. So element wise, it has to be equal, right? So I can find that. You might find that some of those, so remember the problem with inverse kinematic, there might be more than one theta. That is the solution. So you have to solve it together. You have to look at what you get. You can't just run your robot because you might break it. Okay? But does the process make sense? You won't have to do this by hand. You can use your codes, right? So you basically should have the code for each part in your previous code. You just have to manipulate from, right? So we have done examples for the geometry. From there, we came to analytical method. The geometric helps us with the position, but we already basically in your page 2. When I asked you to find the axes and angles for rotation. So what you basically did was an inverse kinematic. Very subtle. All right. So the third method is numerical method, where your robot is complicated. If you have more than 6, you could have well, as many joints as one for a robot, right? And you can find the analytical solution for this part. Then you can solve through numerical method. Now, what do you think your approach would be for numerical? Let's say I give you the problem, find inverse kinematic. When we say numerical method, what does it mean? Yes? No? My graduate student? Continuous, discretized. So when we are solving an analytical method, when we find a solution, everything we can find theta or something, right? Sometimes problems are that we can separate and we can discretize. And then we solve for every single one of those. Let's say theta 1 is 5 degrees, then becomes 6 degrees, and 7 degrees, you solve for all of them. Because it's easier to discretize and solve for that. And we basically, whenever we say numerical, we think of coding. But we have steps that we can find the future based on the information from past. And the step that we define. That's our numerical. Okay. Basically, you tell the computer solve this until you find the solution. And sometimes you don't find the solution because the solution doesn't exist, for example. I'm thinking where in your program you would have to use numerical methods. Do you have a course that's called numerical? Yes? Then you know what I'm talking about. You guys are so mean. Okay, so what did they teach you in your numerical course? They don't teach you. No, I'm serious because I need to know like what is your background? Great. And
Like
Newton Raphson. Okay. All right. Well, I'm sorry to see you, student, and I'm happy to introduce this method to you right now. If you're lucky, you have to have a perfect PA sign because you are without design. Here you see, you can make it. All right. So, I don't want to teach you this numerical. Well, it's not the place. You're supposedly know if you. Well, 3 years ago, when this was not a minor, then you would have had the prereq. Since this is a minor, they took all the prereqs. This is not part of the grade or anything, right? So no stress. This is just a new method. So the Newton-Raphson, so there are two usually common algorithms to solve iterative groups. So one is the Newton-Raphson, then the other one is Jacobian transpose using gradients and search algorithm, right? Like I can see the smokes out of your head. So let's say we set our so x of d, x of desire, right? To be a vector in a Cartesian coordinate meaning x, y, z, so it's the position, and the forward kinematic for any manipulator would be a function. So GQ would be 0 if your x desired is where your robot actually is, right? There's no error. So instead of solving for one, you say, I'm gonna look at the difference. If what I found is equal to what it should be, and the difference is 0, you're good. If there was an error, you try to minimize that. Now you have two different ways of doing that. One is Newton-Raphson, the other one is the Jacobian transpose. So instead of solving for inverse kinematic, you actually solve for this. Try to drive this one to 0. So for a desired joint variable, you want to see if that function is equal to that desired position or that desired vector. If it is 0, if it's not, you keep solving until that number goes close to 0 or 0 if you're lucky. Your book has the Newton-Raphson method. So if you are interested, follow your book. And for the Jacobian inverse, I'm not sure if your book has the Jacobian inverse, does it? Can you take a look? I'm not sure, I don't remember, but that's the okay. So since we already talked about Jacobian, I brought this. So I found from your book and another book, there's a different books there. But since we already seen Jacobian, what was Jacobian mapping between the input and output, right? So we will be able to use that now. You remember Taylor series? Okay, so we're going to use that. We're going to write our function in Taylor series and get rid of higher order terms. And basically, when we get rid of higher order terms, we are not solving the exact problem. We're very close, right? So we know that there will be some errors, but acceptable. So that's why modeling, you always are making some assumptions. So the assumption is like, let's simplify this, get rid of the higher order term, so make it a linear problem. When we can do a linear, when we have a, let's say, continuous problem, and we want to look at small pieces and we want to solve that linearly, we need to make sure that those two operation points are close enough that there is no like dip in between. So it's like a linear solution. That's basically what we're trying to do. So again, x of these, x of desire of the forward kinematic function if the inputs were the desired term values. All right. The Taylor expansion would be Taylor series expansion would be f of q is fq desired, right? Where we want to be plus the Jacobian of q desired minus times q minus q desired plus high order terms, and then we can get rid of this part and we can say that q desired minus q, and because there's a negative in there, j inverse of those q, x desired minus f of q. I'm not wrong. Yeah. Now, to solve that, we are gonna use indexing and look at the previous solution and solve for the next one. So solve it for the first step, then solve it for the next step, for the step after. Raise your hand if you're lost and be honest. Everybody else understand what happened. Okay. All right. Explain to me what the Jacobian inverse method.
So what it is, you have your initial function. Based on that you take a guess if they would give one, take a base set guess, and then based on your n values, you get a new guess, and then you just it'll it through it and you'll get slowly closer.
Yes. Or you get favor. Always converted, right? Yes. So you basically start from educated guess and put in the equation and say, okay, let's solve. And see if I get the desired position through the forward kinematic. If you didn't see how far, what is the difference, then you go and use that difference and you try to iterate until you get to a solution. Now, sometimes you might not converge, you might diverge. You have to then see that in your algorithm and that being able to shut off the problem, the program, otherwise you will not work. All right. So I'm gonna keep this for another time. All right. And the reason being, I think, well, I do have an example at the end, but I don't think like any of those will stay with you. I need to think about it. Like maybe bring an example and do like coding problems here so you all understand. Or for now, just forget about the environment. Until you get a PSI and you have to use the bridge. Because otherwise, all right. So that would be the end of today then. I think you will have it for this, right?
Yeah.
Yeah. So if you looked at the annotated version, there is an example that I will like. There's a solution for a 2-hour robot using this method. So if you wanted to go and look at it, do so, but I will figure out what's the best way to teach this. Because this was not good. All right.